You and I share a sky that looks complete, yet most of what holds it together is invisible. Gravity pulls on stars and gas with a steady hand, but the hand seems much heavier than the light we can see, and that mismatch is the beginning of our story. Today you will learn how we know there is unseen mass, what it might be, and how it shapes the past and future of galaxies, clusters, and the web of the universe. Start with a simple question you can carry in your pocket. If gravity is the glue, why do stars in a spiral galaxy spin so fast without flying away? You would expect stars far from the center to move more slowly, the way planets slow down as they orbit farther from the sun. But measurements show the speed stays roughly flat, almost indifferent to distance. The light says the mass drops off, yet the motion says the mass keeps going. That contradiction is not a small detail. It is a crack that runs through the entire picture. A spiral disk needs far more mass than the glowing stars and gas can supply to keep those outer stars bound, so something unseen extends beyond the starlight and deepens the gravitational well. Astronomers gave the placeholder a plain name on purpose: dark matter, meaning matter that does not shine. Notice how the argument depends on a clean comparison between light and motion. Light tells us how much normal matter is there in the form of stars and gas, while motion tells us the gravitational pull. When those two stories diverge in system after system, you either change what is pulling or you rewrite how gravity works on these scales. You can watch this mismatch most vividly in the rotation curves of many spiral galaxies. A rotation curve is simply a plot of orbital speed against distance from the center, and the flat shape of the curve whispers that mass is not concentrated in the bright core, but spread throughout a wide, faint halo that extends well beyond the visible disk. The starlight fades, yet the tug remains, like hearing footsteps continue after the hallway light turns off. The same pattern shows up on larger scales inside clusters of galaxies, which are giant cities of galaxies held together by their shared gravity. If you estimate the mass of a cluster by counting the visible matter, you fall short. If you estimate by the motions of the galaxies inside the cluster, you find far more mass than the light can explain. The cluster acts heavy even when the lamps are dim. There is another way to weigh the invisible, and it uses the bending of light itself. Massive objects curve space, and curved space bends the path of light, so a galaxy cluster can act like a lens that distorts and magnifies the view of background galaxies. When astronomers map that distortion, they trace the gravity directly and draw a picture of where the mass truly sits. Time and again, the gravity map sketches structures that outstrip the bright matter. One famous collision of clusters shows a striking separation between the hot gas and the mass that lenses the background galaxies. The gas slams together and slows down, but most of the mass sails through and keeps going, as if it barely notices the crash. That behavior matches matter that interacts weakly with itself and with ordinary matter, yet still obeys gravity faithfully. The picture is not perfect proof, but it is a clear fingerprint. Before we go deeper, draw a clean line between two common confusions. Dark matter is not the same as dark energy. Dark matter pulls together by adding gravity without shining, while dark energy appears to push the expansion of space to speed up over vast distances. One adds extra weight to structures, the other shapes the global expansion. They are different clues in the same cosmic investigation. We still need to ask a careful question. Could the law of gravity itself need a tune-up at the scales of galaxies? Some researchers have proposed changes that make gravity effectively stronger when acceleration is tiny, which can fit certain rotation curves with fewer moving parts. A modified law can be a useful lens on the data, and it is wise to test the simplest change before inventing unseen stuff. However, the universe hands us multiple, independent rulers and clocks, and whichever story we accept must work for all of them at once. The same unseen mass that keeps spiral disks from flying apart also helps explain the way galaxy clusters bend light, the way the earliest light patterns in the sky set the ratio of matter types, and the way the large-scale web of galaxies grew from small seeds into sheets and filaments. A single fix to gravity struggles to match every one of those arenas without new complications. Think about the oldest light we can measure, the faint microwave glow that fills the sky in every direction. It carries tiny ripples in temperature and polarization that are fossil records of the infant universe. Those ripples encode how much normal matter, how much invisible matter, and how much radiation were present when the first atoms formed and the fog of charged particles cleared. When you fit those ancient ripples with the physics of sound waves and a hot plasma, you find that normal matter alone cannot seed the cosmic structures we see today. You need a form of matter that does not feel pressure from light, that clumps early and that moves slowly enough to pile up into the deep wells that later guide gas to cool and make stars. In plain words, you need a cold, invisible scaffold. The picture that emerges is practical. A vast, roughly spherical halo of unseen mass surrounds each galaxy, and that halo stretches far beyond the bright disk or bulge. Gas cools and condenses inside this halo. Stars ignite, and feedback from those stars and from black holes in the centers stirs and heats the gas. But the deeper shape and depth of the well come from the dark halo. The visible galaxy is a lantern hung inside a larger frame. You might wonder whether the unseen frame is made of familiar stuff in a hiding place we have not yet searched. Could it be cold? Clouds of faint stars, dead embers, or clumps of planets without stars, drifting in the dark? Decades of searches have looked for the telltale winks when such objects pass in front of background stars and cause a brief brightening, and the results tell us that these ordinary bodies cannot make up more than a small fraction of the missing mass. The same conclusion comes from looking at the glow of the earliest light and at the abundances of the simplest elements forged in the first minutes after the hot beginning. There is a ceiling on how much normal matter the universe can have while still matching those observations, and the ceiling is too low to account for the gravity we measure. That pushes us toward a new ingredient, not a hidden stash of the familiar. So what could the new ingredient be? One path points to a new type of particle that rarely interacts with light or with ordinary matter but contributes mass. A popular idea has been a weakly interacting, massive particle, a mouthful that simply means a heavy particle that barely notices the electromagnetic force. Such a particle would move slowly in the early universe, form the needed scaffold, and leave subtle traces today. Another path points to a feather-light particle first imagined to mend puzzles in the behavior of the strong nuclear force. This particle, often called an axion, would be so light that unimaginably many could form a cold, coherent background, more like a field than a gas. If such a field exists, it can act as dark matter by adding gravity without shining, and might leave a narrow band signal that careful experiments can chase. Neutrinos, the ghostly particles that stream from nuclear reactions, certainly exist and carry mass. But their low mass and high speed in the early universe mean they wash out small structures and cannot be the main ingredient of the unseen scaffold. They are part of the story, but not the main cast. That distinction between the existence of a thing and its sufficiency is a recurring theme in science. There is also the bold thought that some of the dark mass could be black holes born in the early universe, long before stars formed. These would be black holes made not by dying stars, but by extreme density, ripples that briefly trap themselves. Observations of how light flickers when compact objects pass in front of stars, along with the details of the oldest light and the distribution of small galaxies, put strong limits on this idea. A small share might still be possible in some mass ranges, but the dominant share is unlikely to be early black holes. How do we search for new particles that refuse to shine and rarely touch us? We build quiet rooms deep underground, far from cosmic rays, and we wait with patient instruments. In one approach, a tank of ultra-pure liquid xenon records tiny flashes and whispers of charge when a passing dark matter particle jostles an atomic nucleus. In another, crystals cooled to nearly absolute zero register the faintest vibrations from a knock at the lattice. We also look to the sky for secondary signs. If dark matter particles can occasionally annihilate or decay, their end products could include high-energy light or charged particles. Space telescopes and balloon experiments watch the center of our galaxy and nearby dwarf galaxies for excesses that do not fit the usual astrophysics. The evidence so far is suggestive in places and challenging in others, and the sky insists we keep our models honest. Particle colliders add a third angle. When protons slam together at tremendous energies, they can produce heavy, unseen particles that slip through detectors, leaving a missing energy pattern in the debris. Engineers and physicists design searches that look for the right mix of visible particles, plus a missing chunk of momentum that points to something that refused to light up the instrument. A null result is not a defeat. It is a map of where the quarry does not live. Simulations help us turn the clues into a working map of structure. Start with a universe filled with a nearly uniform mix of dark matter and ordinary matter. Add tiny ripples measured in the oldest light, then let gravity run on a computer for billions of years. The invisible matter collapses first into clumps and filaments, a spiderweb across cosmic distances, and the ordinary gas flows along that web, cooling in the densest knots to make stars and galaxies. The web matches the phone-like pattern we chart in galaxy surveys. Yet a good map does not mean a perfect map, and there are puzzles in the details that keep the field lively. The centers of some small galaxies look less dense and more flattened than pure dark matter simulations would predict, a mismatch known as the cusp versus core problem. The number of small satellite galaxies around a large host looks lower than naive early predictions suggested, a mismatch called the missing satellites problem. Real gas, real stars, and real explosions are messy, and when you include their heating and stirring, some of the tension eases. Star formation and black hole feedback can push gas around with enough force to tug on the dark matter distribution, gently carving out a lower density core over time. Tides from a large host can also strip small galaxies and dim them until they are hard to see, which narrows the gap between predicted and observed counts. Each of these effects is an invitation to refine both the astrophysics and the searches for dark matter's particle nature. Modified gravity deserves return visits in this tour because it captures certain galactic regularities in a compact way. There is a plain relation between how much normal matter a disk contains and how fast that disk rotates, and a change to how gravity behaves at very low accelerations can write that relation directly into the law. But when you apply the same change to clusters, to the bending of light, and to the oldest light patterns, you must add unseen mass back in to make the numbers work, which blunts the original simplicity. A healthy field keeps live alternatives near the table while betting most of its chips where the independent evidence points. Right now, the weight of that evidence favors an invisible matter component that adds gravity without light and that moves slowly enough in the early universe to seed structure on small scales. That does not end the search, it sharpens it. It tells us what kinds of experiments deserve extra patience, and what kinds of signals would count as a watershed. You might ask how we can be sure this unseen matter does not interact at all except by gravity. The honest answer is that we are not sure. We are narrowing the possibilities. Some models allow for a feeble interaction with ordinary matter that shows up as a rare knock on a nucleus, or a faint change in how heat moves through a crystal. Others allow for a hidden sector with its own forces that mostly ignore our light but still shape their own subtle dynamics. There is a common worry that the phrase Dark matter is a way of papering over ignorance. In science, a placeholder is a promise to test, not a license to drift. The term dark matter says, we see the effects, we can chart them, and we will update the guess with the best available evidence. Every new survey and every new instrument forces that placeholder to earn its keep, or to surrender it. Consider what happens if you remove dark matter from the story and try to grow the web with ordinary matter alone. In the early universe, ordinary matter is glued to light through the electric force, which supports pressure waves that resist collapse on small scales. Without a collisionless, pressure-free component to anchor the wells, you would struggle to build galaxies as quickly and in such abundance as we see them today. The fossil sound waves that we map in the galaxy distribution also favor an invisible mass that does not feel light's pressure. The invisible scaffold is not just a background player, it also shapes the delicate dynamics inside galaxies. It can stabilize disks, alter how bars and spiral arms evolve, and set the stage for the dance of satellites that merge over time to build larger systems. When a small galaxy plunges through the halo of a giant, tides tear at it and streams of stars stretch out as ghostly arcs, and those streams trace the unseen gravity like chalk dust in a draft. Gravitational lensing has become a cartographer's tool for this hidden terrain. Weak lensing, the subtle, statistical stretching of many background galaxies, lets us measure how mass clumps on scales from galaxies to the cosmic web. Strong lensing, the creation of arcs, rings, and multiple images by very massive structures, lets us weigh the cores of clusters and probe the shape of halos. Each of these methods works without assuming anything about how stars form or how gas cools, which is why they carry such weight. New instruments are giving us sharper maps and faster counts. A space mission devoted to measuring the shapes and distances of galaxies across a wide swath of sky is beginning to deliver data that can tighten our constraints on how mass clumps over time. A ground-based telescope named for a pioneer of galaxy rotation work will conduct a survey that reads the night sky in rapid, deep exposures, catching transient events while also building an exquisite map for lensing studies. Together, they will either confirm our current picture with greater precision or point to cracks that demand new physics. If the invisible scaffold is made of weakly interacting massive particles, the next leap forward could be a direct detection in an underground detector that sees a clear annual pattern or a sharp spectral feature across multiple targets. If the scaffold is made of an axion field, the breakthrough might be a narrow, radio-like tone that sweeps as an apparatus tunes through frequency space, or a tiny twist in the polarization of light that passes through a magnetic field. Each path has a decisive signature in mind. The most powerful habit you can cultivate as a learner is to follow the chain of evidence across methods and scales. Ask what rotation curves say. Then ask whether lensing agrees. Then ask whether the oldest light and the galaxy web agree with both. A picture that holds together at every rung is rare, and dark matter has earned that coherence more than most ideas in modern astrophysics. Still, humility belongs in the kit. The universe has surprised us before, and our words are scaffolds, not walls. When you hear a claim that everything can be explained by changing gravity alone, look for a clean test with the oldest light or with lensing in clusters. When you hear a claim that a particular particle has been found, look for a second method that can confirm the signal independently and in a new regime. Here is a small exercise that pays off. Take a spiral galaxy image and sketch a circle halfway out in the disk. Then another near the faint edge. Write down what you would expect the speeds to be if the only mass were the bright stars. Then recall that the measured speeds are nearly the same at both radii. That one comparison captures decades of work and points directly to the need for a halo. Another exercise lives in the way clusters wear arcs of light. Find a picture of a lensing cluster that shows blue arcs wrapped around a massive core. Then remember that those arcs reveal a ring where the lens is strong. The size of that ring and the pattern of arcs let you weigh the mass inside. With a ruler that light itself supplies, when the weight you get exceeds the light by a wide margin, you have learned something no single star count could teach you. The invisible scaffold even whispers in the distribution of satellite galaxies. Some satellites orbit on similar planes. Some show streams that remember a past encounter, and some are missing where early models predicted many. Each detail is a constraint on the mass and shape of the halo, the stirring from past mergers, and the mild pushes from feedback. When you see a stream stretch across the sky, you are reading the handwriting of gravity, not just a pretty trace. Dark matter halos are not featureless spheres. They are triaxial, meaning they have 3 different axis lengths, and they twist and grow as mergers happen. The inner part can be more rounded where stars contribute to the potential, while the outer parts retain the sharper memory of recent accretion. Substructure lives within, like small knots in a larger rope, and those knots can lens background sources in ways that reveal their presence without any light at all. Whenever you feel overwhelmed by the names and methods, come back to the core logic. Gravity is a measurement, not just a theory, and motion is the way the universe reports that measurement to you. When the motion says one thing and the light says another, believe the motion and ask what mass could be hiding. Then, test that answer against every other report the universe is willing to give. There is poetry in the idea that the night sky's shape depends on something we cannot see and might never touch directly. Yet the poetry is not an excuse to stop. It is a reason to build better instruments and to imagine better questions. Wonder is a renewable resource in science, and dark matter is one of its most generous wells. Soon, surveys that scan the sky again and again will let us watch the subtle drift of many galaxies' apparent positions, a dance called proper motion across cosmic distances. Combined with lensing and with the pattern of large-scale structure, that drift could trace how mass moves and clumps in a way that is not possible with a single snapshot. Motion over time is the deepest story a map can tell. Galaxies are not isolated islands. They live in filaments fed by streams of gas and dark matter. When 2 galaxies meet, their halos meet first, and the outskirts begin to tug and stir long before the bright disks overlap. The timing and texture of these encounters leave marks in the stars, in the gas, and in the lensing map, and each mark lets us back out the mass and softness of the halo. Star formation itself is a negotiation with gravity set by the halo's backdrop. A deeper halo keeps gas bound and can recycle outflows back into the disk, prolonging star birth, while a shallow halo can let outflows escape and quench a small galaxy early. That is why the same feedback process can produce different outcomes in different systems. The unseen frame sets the stage for the visible play. When you see a dwarf galaxy with very low surface brightness, almost a whisper of starlight across a large area, you are looking at a system where the halo outweighs the lantern by a wide margin. These galaxies are excellent laboratories for the nature of dark matter because their stars contribute little to the central gravity. So the mass profile you infer mostly belongs to the invisible component. They turn down the glare and let you see the scaffold more clearly. The future of the field belongs to synthesis. Direct searches underground, signals in the sky, collider experiments, lensing maps, satellite streams, and the oldest light will all speak, and the winning idea will be the one that lets those voices harmonize. A single dramatic claim will not be enough. We will want a choir that sings the same tune from different angles. Until then, you can hold a working picture in your mind that is both simple and strong. The universe is threaded with an invisible web that formed first. Normal matter fell into that web to make galaxies and stars. And the details we see today are the result of that long dance mixed with the fireworks of star birth and the tempers of black holes. Each new map is another stanza in the same song. If you take one sentence with you, let it be this: gravity is honest even when light is shy. When you read a headline about a survey tightening the map of mass, or an underground detector lowering the possible strength of a particle's interaction, or a telescope catching a sharper ring of lensed light, translate each into the same language. We are learning the weight and shape of the invisible frame that holds the sky together. Some people feel uneasy when they hear that most of the mass in the universe is dark. The feeling is human. It sounds like ignorance writ large. But knowing the outline of what we do not yet know is progress, not retreat. We now have a stable, testable picture that connects galaxies, clusters, and the cosmic web. And we have multiple routes to push that picture until it breaks or stands taller. Your curiosity is part of the instrument. Ask how we measure mass. Ask how we separate what light tells us from what motion tells us. And ask what predictions a specific idea makes that we can check. In that practice, you join the tradition that turned faint smears on glass plates into a census of the unseen, and you earn a new way to read the night. The next time you step outside after sunset, find the faint band of the Milky Way where darkness returns the sky to itself. The arc is a visible trace of a much larger, invisible halo that cradles our galaxy. Around that halo, other halos drift, and the web between them pulls on all of us with a steady hand we can weigh, even if we cannot see it. The modern trail opens with a handful of careful measurements that refuse to behave, and each one carried a human name that mattered. Jen Ort weighed the Milky Way's local stars and found extra pull. Fritz Zwicky weighed a swarm of galaxies and cried missing mass, and Vera Rubin mapped whole disks and made the flat curve undeniable. Those names are more than history flashcards. They are reminders that progress often begins as a quiet mismatch on a graph. A straight edge touching unexpected points forced new questions, and the bravery was in not sanding the data to fit an old story. You can honor that bravery by keeping your own straight edge honest. When Vera Rubin and Kent Ford tracked the speeds of stars and gas far from galactic centers, their spectrograph slit crossed faint outer arms like a ruler laid along a ghost. The starlight thinned with radius, but the Doppler shift held firm, saying the edge refuses to slow. Gravity was telling on itself. To translate that into mass, you use a simple rule. In a stable orbit, speed squared over radius balances the inward pull. If speed stays flat while radius grows, then mass enclosed must rise with radius long after the light has faded. The only way to do that cleanly is a broad, dim halo. Cluster evidence reads the same music in a different key. Galaxies in a cluster move with wide velocity spreads, as if the city's gravity well were much deeper than its lit skyline suggests. Add hot X-ray glowing gas bound within and lensing of background galaxies, and three instruments sing a harmony that light alone cannot carry. Gravitational lensing deserves a slow, plain description because it turns geometry into a scale. Mass curves space, straight paths become arcs, and circles appear when alignment lines up just so. Measure the arc radii and the gentle shear of many background galaxies, and you infer the distribution of mass that must be present. In famous merging clusters, the hot gas slams and lingers in the middle, glowing in X-rays, while the lensing mass peaks glide ahead with the galaxies. That separation is hard to fake by just tweaking gravity's law, because the different components behave differently during collisions. Matter that barely bumps into itself explains the glide. The earliest light, called the cosmic microwave background, carries acoustic peaks that are fossil sound waves frozen when the young plasma cooled into neutral atoms. The spacing and heights of those peaks tell you how much ordinary matter there was, how much unseen matter there was, and how fast the early universe was expanding. Ordinary matter alone cannot fit those peak patterns and still grow the web we see later. You need an additional component that does not feel pressure from light, begins clumping early, and seeds wells deep enough that gas can fall in after the fog lifts. That component behaves like cold, dark matter. Big Bang element making, the brief furnace of the first minutes, sets tight limits on how much ordinary matter can exist without spoiling the measured helium and deuterium. Those limits leave most of the gravitating mass unaccounted for if you restrict yourself to protons, neutrons, and electrons. Again, the sky points past the familiar. Let us walk through candidate natures with a clear yardstick. What do they predict that you can measure? A heavy, weakly coupled particle predicts rare nuclear recoils underground, possible faint skies from annihilation byproducts, and missing energy patterns in high-energy collisions. A feather-light, wave-like particle predicts interference, scale patterns in small galaxies, and narrow radiotones in tuned cavities. Underground detectors have become cathedrals of stillness. Tanks of liquid xenon or liquid argon sit in deep caverns, wrapped in layers of shielding, listening for single quanta of light and charge. The background drips lower each year, and the silence itself carves away. Large regions of possibility space. Cryogenic crystals tell the same story with a different sense. At temperatures near absolute zero, a single nuclear jolt sends a whisper through the lattice that exquisitely sensitive thermometers can hear. Two channels, light and heat, or charge and heat, allow discrimination between true knocks and imposters. For the wave-like path, a magnetic field and a resonant metal cavity act together as a kind of radio for the invisible. By slowly tuning the cavity, experiments search for a narrow signal that would appear if the ambient wave-like field converts into a photon. It is an auditory image, sweeping the dial across static to catch a tone. In the sky, the center of our galaxy is a tempting theater because densities there are high. But it is also a messy stage packed with astrophysical actors. Nearby dwarf galaxies, dim and dominated by unseen mass, are cleaner targets. Their quiet makes any excess glow stand out. A true signal must repeat with the same shape across multiple such objects. Colliders add a complementary test by pushing energy into new territory and watching what refuses to appear. When invisible particles carry away momentum, the visible debris recoils in a pattern that does not add up to zero. You look for balanced books and celebrate when you find a ledger that will not close. Simulations that include both unseen mass and gas physics now grow galaxies that look and behave close to what telescopes observe. Outflows from supernovae and from central black holes stir and heat the gas, thickening disks and bending rotation curves in ways that bring small-scale tensions into alignment. The message is not that any model will do, but that the messy middle matters. Some researchers explore the idea that the unseen matter occasionally bumps into itself with a small cross-section, which would let the inner parts of halos become rounder and less dense. In this self-interacting picture, clusters and dwarf galaxies together set tight bounds, because the same physics must explain both the largest and the smallest labs. Others test a warm variety of unseen matter that moved a bit faster in the early universe, and so erased the tiniest seeds. This shifts the expected number of low-mass galaxies and the sharpness of inner density peaks. Lines seen in the absorption of distant quasar light by intergalactic hydrogen become rulers for this idea, because they trace small-scale structure along long sightlines. An ultralight, wave-like field pushes the imagination further by making the de Broglie wavelength galactic in size. In that case, the center of a small halo can resemble a soliton-like core, smoother than particle pictures predict. Star streams and the shapes of dwarf galaxy centers become the measuring sticks for that wave imprint. History shows that multiple ideas can survive early tests, but only one earns the right to be called the standard when independent lines converge. Today, cold, unseen matter that barely interacts is the workhorse because it explains the web, the lenses, the clusters, and the oldest light with one ingredient. That is a high bar, and habits of humility keep us checking. You deserve a tactile picture of a halo. Think of density falling with radius in a way that is steep near the center and gentler outside. Built from the layered memory of many mergers, sub-halos orbit within, each with its own tiny history, and their tides pull at passing star streams to leave gaps and wiggles that betray their mass. The Milky Way's own streams, such as the long ribbon from a torn dwarf galaxy and the slender trail from a disrupted cluster, are not just pretty arcs. They are seismographs for gravity, sensitive to every small tug along their length. When a stream shows a clean gap or a folded spur, you can back out the mass of the unseen hand that made it. Disk galaxies also grow bars, elongated stellar structures that transfer angular momentum and reshape the inner regions. The rate at which a bar slows and how far it reaches depend on how much invisible matter lies inside the luminous part. Bars therefore act as clocks and yardsticks at once, timing the friction between stars and the halo. Galaxy groups, smaller cousins of clusters. Let us test dynamics where ordinary matter plays a larger share, yet the unseen still dominates. The orbits of satellites, the temperature of intragroup gas, and the weak lensing signal together narrow the plausible shapes and normalizations of halos. It is a habit now. Never trust one witness alone. On the largest scales, the galaxy distribution shows gentle ripples in its 2-point statistics that are the grown-up cousins of the early acoustic waves. Those ripples act as a standard ruler that tracks how distances scale with time. The agreement between this ruler and the story told by the oldest light is one of the quiet triumphs of modern cosmology. Imagers in space and on high mountains deepen and sharpen these statistics by measuring the weak lensing shear of billions of galaxies. Alignments that would otherwise average to zero reveal a net pattern caused by foreground mass. From this, we infer how clumpy the universe is today and compare it with expectations grown from the earliest seeds. A curiosity that often puzzles newcomers is why the rotation curves of very different galaxies look so self-similar once you scale radius and speed. The reason is layered. Halos assemble in a near-universal way. Disks settle where the gas can cool and conserve angular momentum, and feedback sculpts the inner slope. Universality rises out of diverse histories. Lopsided features, warps, and flares in outer disks are not mere decoration. They often betray recent minor mergers or ongoing accretion along filaments, and the resilience of the disk depends on the supporting halo. A stiffer, heavier halo resists deformation. A lighter, puffier halo allows the outer parts to ripple longer. Measurements of the vertical motions of stars near the Sun let us weigh the local column of mass through the disk. The result exceeds the tally of visible stars and gas by a modest but firm amount, pointing again to a dark contribution in our neighborhood. Local and global measurements rhyme, and that rhyme builds trust. Beyond individual systems, you can ask whether unseen matter clusters exactly where ordinary matter does. It clusters more broadly and earlier because it does not feel the pressure of light, but gravity eventually pulls gas into the same wells. Where radiation and winds complicate the gas, lensing cuts through the fog and shows the common backbone beneath. A measured mismatch between predicted and observed small-scale structure remains a living probe. If future star counts and stream maps show fewer or smoother subhalos than the basic particle picture predicts, That would push us toward either self-interaction or wave-like behavior. Precision, not drama, will choose the path. The language you use shapes how you think, so keep your terms clean. Dark matter is an inference from gravity, not a direct detection yet. And that is acceptable because multiple inferences point to the same hidden actor. Confidence grows with consilience, the joining of independent lines. As for meaning, do not let the word dark trick you into picturing a gloomier universe. The term is simply bookkeeping for everything that fails to interact with light in familiar ways, but participates in the structure and motion we measure. In a sense, the universe is generous. It shows its hand through gravity even when it keeps its light to itself. New surveys will soon deliver maps that reduce statistical noise until subtle systematics become the main challenge. Teams will cross-check shear with galaxy clustering, cross-check distances with supernovae, and cross-check masses with dynamics. The prize is not a headline, but a high-fidelity portrait of the invisible scaffold. Alongside the skywork, instrument builders push underground thresholds lower by pairing different target nuclei and by learning the fingerprints of every background. Seasonal modulation, multiple scatter rejection, and precise position reconstruction. Let true signals stand out if nature has placed them within reach. Patience is part of the method. Theory remains busy too, tightening predictions for how halos respond to bursts of star formation, how black hole feeding cycles puff up or compress central regions, and how different unseen matter models alter those responses. The last mile of inference often runs through the complex lives of galaxies. If a clear particle signal appears, the first task will be to measure its mass and interaction strength in more than one way. The second task will be to fold that knowledge back into how halos form and how galaxies evolve, closing a loop from particle physics to cosmic architecture. That loop is the quiet dream behind decades of patient work. Until that day, you can hold a robust, testable picture. Galaxies live inside massive, extended halos of non-luminous matter. Clusters and lensing maps weigh more than the light can explain. The oldest light and the element ratios demand more gravitating matter than protons and neutrons can provide. Each line meets the others like beams in a strong frame. Walk outside again and let your eyes adjust to the dim band of our galaxy. Somewhere above you, a star stream threads the halo like a pale scar, a memory of a small companion pulled apart. You cannot see the hand that made the scar, but you can trace its strength, and that is a kind of seeing. If you love clean tests, keep an eye on cold, dim dwarf galaxies near the Milky Way. Their brightness is so low that the stars do not muddy the gravity field, and their motions offer a near-direct reading of the halo profile. Any new physics that softens the central density will reveal itself there first. If you prefer geometry, follow strong lens systems that show multiple images and tiny flux anomalies. Those small brightness mismatches can be caused by subhalos near the light path, acting as hidden weights on the lensing scale. By collecting many such systems, we can weigh the population of small clumps without ever seeing their light. And if you enjoy time series, the repeating cadence of surveys will let us see lensing systems change as sources vary, giving time delays that measure distances and lens masses at once. The precision of those delays turns into precision on the mass map, which in turn sharpens what we allow for the unseen. Through all of this, remember the method that got us here. Compare independent measures. Prefer the simplest picture that fits them all, and be ready to trade pride for accuracy when the sky votes. You are not just learning facts. You are learning a way of seeing that keeps its promises. The universe is not hiding on purpose. It is simply bigger and older than our first guesses, and it contains forms of matter that are quiet in light but loud in gravity. With patience, we can hear that gravity clearly enough to sketch the unseen and, one day, to name it.